All right, so let us keep going. Today's topic is going to be discussing how the Earth was weighed. And now for the disclaimer. So as I talk about these experiments, this is all running basically from my memory, and so there may be some mistakes in the stuff that I present, but they should be relatively minor mistakes. In general, the physics is what's most important, like how the thing operates. We'll be talking about some experiments that were done way back in the day, like 1700s, in order to determine the mass of the Earth, because a number of things, important characteristics of the gravitational force that need to be addressed, that lead into a whole host of gravitational experiments that have been done for centuries now. So with gravity, let me put it another way. Newton's second law says that forces cause acceleration. Forces cause acceleration. And Newton also, when he devised his theory of gravity, gravity gives you a force. It is not. Okay, I'm back. I'm sorry for that delay. Got it. Insert Jeopardy music right there. All right, so back where we were. Newton's laws. So the second law, this is basically how you map things mathematically onto, how you map something mathematically into mathematical equations so that you can then make predictions based upon what you find. That's what Newton's laws are. His law of gravity is a force. It basically tells you what you can put into this part of the equation, this force part of the equation. And what he found, or what he devised, was that the force of gravity is proportional to, with the constant of proportionality big G, the mass of the Earth, or the mass of one object times the mass of another object divided by the separation of the two objects squared. So this is the separation along a particular line. Okay, so this is the force of gravity, and this right here would feed into that part of the equation. So what does this do? So that would cause something that looks like this. That would say that G, the mass of two objects divided by their separation squared, causes one of those objects to accelerate. And then if you may be wondering, like, what about the other mass? Well, if you're interested in the other mass, then you put the other object's mass right here, and you'll find its acceleration. So this is a force. It's the same force on both objects, except equal and opposite in direction. And so if you want to know how the other mass accelerates, then you just replace this little m with a big M, and then that will give you the acceleration on the big, whatever mass goes with the big M. Anyways, so this is how you take gravity and you put it into Newton's laws, and then you have to solve this to figure out what is the acceleration of this particular mass. Now, there are a variety of interesting implications of this formula, one of them being the fact that this m right here and this m right here appear to be identical. That if you divide both sides by that quantity, then it drops out, which means that the acceleration of any object is independent of the mass of that object. In fact, independent completely of the composition of that object. So that's the statement now that would be called the equivalence principle. It's that would be an interesting thing to test. If gravity really is directly proportional to the mass of the object that is accelerated by that force. That's not an obvious thing. It's certainly not true with any other of the forces of nature, but for the moment, we're not looking at that. Instead, what we're looking at, so equivalence principle things is something we will cover in future streams. But for now, we're going to accept the equivalence principle, the fact that this mass right here cancels this mass right here, and instead focus on the remaining quantities. So these things right here, that the acceleration due to gravity is this fundamental constant G, the mass of the object divided by the separation of the two objects squared. Now, if you're a person standing on the surface of the Earth, what that says is that the acceleration of some object is proportional to the mass of the Earth divided by the size of the Earth squared. The problem is that these two quantities here, the G and M, always come together. They always appear as a product and not as, like, there's no G plus M anywhere in the equations. It's always G times M. And so how do you separate the mass of the Earth from this fundamental constant? How do you measure this fundamental constant? Now, to be fair, at the time, it was just assumed that the acceleration due to the Earth was a constant, like this little g was a constant, the 9.81 meters per second squared, or 32 feet per second squared, was a constant, and therefore you can rewrite this this quantity here using the density of the Earth. And so what Cavendish originally set out to do was to measure the density of the Earth, not so much to measure big G. Turns out that the two are equivalent. If you measure one, then you've measured the other. But today, when we do new experiments to measure big G, it's not to measure the density of the Earth. It's in fact to measure the Newton's constant right here. So Newton's constant. So we're going to project our current sensibilities back 200 and something years onto Cavendish, who is going to be doing the first experiment to measure big G, and as a consequence to be able to measure the mass of the Earth. So the only way for us to measure the mass of the Earth is for us to know what this gravitational constant is. There's no way to predict it. Well, maybe there is a way to predict it, but it has not been predicted successfully yet. And so that's where we currently stand. So the idea was, if you could design an apparatus that, rather than using the mass of the Earth, was where you could measure the gravitational force between two objects where you actually know the masses of those two objects. Okay, and so the design that was proposed, and it was actually proposed by some previous guy, and Cavendish picked up the parts and then kind of rebuilt the apparatus and proceeded with the experiment. The idea that was proposed is that you take two spheres, and there's good reasons to use spheres. Take two spheres like this, and you put them on a torsion pendulum. So you link them together like this, and you suspend it. So a torsion pendulum is a pendulum that, rather than swinging from side to side, it twists. Okay, and it oscillates back and forth in a twisting motion. So torsion meaning twist, and pendulum meaning that it oscillates. So a torsion pendulum twists back and forth. Now, the reason that you want to do a torsion pendulum is that torsion pendula are extremely sensitive, because whenever you have some oscillating object, the frequency of the oscillation is going to be proportional to the equivalent of a spring constant. So let's say that you have a mass on a spring like this. This is going to oscillate up and down, and the stiffer the spring, the faster it will oscillate. If you want the thing to oscillate very slowly, then you want to have a spring that is not very stiff at all. So it's really easy to stretch and really easy to compress. So a spring that is very weak, has a weak coupling, is going to produce very long scale oscillations, and as a consequence it will be very sensitive to any changes in the mass that you put there, because it's easy to stretch, which means that a small change in the mass will cause a large change in the stretch, how much the spring is stretched. So by the same token, if you have a torsion pendulum where you have a thin wire like this, and then you have this bell with some big masses on the side, the spring constant of a torsion pendulum, something twisting, you can make really, really, really small, which means that very, very small forces are able to cause large deflections or large twists of the torsion pendulum. Okay, so you set up a design like this. You set up a torsion pendulum because it's very sensitive to any forces that are on it. If you touch one of these things, it would cause it to swing with large amplitude swinging. And then the idea is that you create another set of masses that you would put next to the torsion pendulum like this. So these ones are stationary. So these are two kind of stationary balls of whatever they might be, probably something like lead. And then you have these balls here that or spheres that are suspended on this torsion pendulum. And then you can set this thing in motion. For example, we'll see how it was actually done, but you could, if you set these things in motion, then you will get some oscillation period. In the absence of these external masses, so if you remove these external masses, you will get one oscillation frequency. Like there will be some oscillation frequency corresponding to the effective spring constant of this twisting fiber. When you put the masses here, when you put the masses back, then there are a couple different things that you can measure. One, you can actually measure the deflection. So you could set these things, you could set these masses down offset by some angle and measure the deflection of the torsion pendulum towards those masses because of the gravitational attraction between the masses on this object and the masses out here. So that's one way you could do it. Another way you could do it, make the same measurement, is now that you have these masses that are right here next to the equilibrium position, they're going to exert a force that is always going to try to pull the torsion pendulum back to align it with these masses. So the pendulum will swing, and it will swing from side, it will twist from side to side slightly faster, because not only do you have the spring force from the torsion fiber, but you also have this additional force from these external source masses that will cause it to oscillate more rapidly. It's almost like there's a second spring. The equivalent would be like a second spring attached between these two things here. And so when it twists away from those masses are going to have an attractive force that's going to pull everything back together. So a spring is it's a gravitational force and not a spring force here. It is a spring force with the torsion fiber. So that is the idea of the Cavendish experiment. You can measure the change in the oscillation frequency of this torsion pendulum, and that will tell you the strength of the force between these two objects here and these two objects here. You get basically a factor of 2, so you divide it by 2, and that gives you the strength of the coupling between this mass and this mass. And since you now have the strength and you know the mass, you know the masses of each of these two spheres, and you know their separation because you can just hold a ruler up to it and measure the separation. The only thing that is undetermined is big G. So that is how the Cavendish experiment was originally designed. And it's been done multiple times over the last centuries, slowly improving our measurement of the gravitational constant. So let me check real quick. Would you be doing this? Okay, now here's the advantage of this type of experiment with a torsion pendulum. With a torsion pendulum experiment here, you've removed the effect of the Earth. So Earth's gravity in this apparatus, so let me redraw the apparatus. So here is the apparatus. It looks kind of like this. Earth's gravity is pulling downwards. And so by suspending it with a fiber, you've eliminated Earth's gravity. You've canceled out Earth's gravity because, yes, there is a force of gravity that's pulling down on this pendulum here, but you also have the string, or the force, the tension in the string or the fiber that's keeping it up. And so Earth's gravity has been canceled out, and you're only left with whatever forces remain, which is going to be the forces between, here's one source mass, here's another source mass, and then here's your pendulum masses, and the gravitational attraction between those two things. So you've eliminated, this is an isometric view. So like here's the plane of oscillation of those things. You've eliminated Earth's gravity, and you're left with only the residual force between the spherical balls of metal that are the source, the gravitational source, and then the pendulum masses that is your detector. Okay, so let us see. We'll take a look now at what did the apparatus look like. Thank you for that subscription. I appreciate that very much. All right, here is the Astronomy Picture of the Day catalog. Where did the Cavendish experiment go? Here we go, the Cavendish experiment. So here is a drawing of the apparatus itself. In this case, they have to have it, okay, yay. The screen is gone. Let us change this real quick. I want that display captured. Pull up this screen. There we go. All right. Now with this image, here's the big torsion pendulum. Here's the two spheres that are there. They have these two smaller spheres that are down here. We'll zoom in to see exactly what's going on with that, but you can see this big torsion apparatus here with these large spheres hanging down from the sides. All right, and then he has this pulley system out here, this K, where he can change the orientation, make adjustments, and there's another one up here as well. Vertical section drawing of Cavendish torsion balance, including the building in which it was housed. So you have to have this in a building. When you do this in a laboratory today, you'll actually have it in a vacuum chamber, because any air currents, any residual air currents is going to cause this thing to blow all over the place. The gravitational force is extremely weak, and so having such a weak force means that any kind of air currents that are flowing through there is going to mess up your measurement. And the only way to do it is to completely isolate it from, well, hopefully you would isolate it from the air in general, but this was before the advent of the turbopump, and so They just have to isolate it in its own building so that no air currents are flowing through, no drafts are coming through. But today you would have a vacuum chamber and you would suck out all the air down to, gosh, you probably would operate something like this at 10 to the minus 8 torr. Or if you did it cryogenically, you could get down to like 10 to the minus 12 torr, which is a trillionth of an atmosphere or something like that. So small, you want as little interaction with the air as possible when you set up an experiment like this. So this is the Cavendish experiment, the design of the experiment. The two large balls were positioned on alternate sides of the horizontal wooden arm of the balance. Their mutual attraction to the small balls caused the arm to rotate, twisting the wire supporting the arm. The arm stopped rotating when it reached an angle where the twisting force in the wire balanced the combined gravitational force of the attraction between the large and small lead spheres. So they were lead, which is what I expected they would be. Now, so this implies that the way that this particular experiment was done, the way that Cavendish originally did the experiment, was to use this as what they call a torsion balance. So it wasn't actually oscillating as a pendulum. Instead, it was sitting there as a balance, and then you would you would move the source masses in such a way that you would induce a twist, and then you knew the torsion properties of the fiber that it was suspended from in order to convert that from the gravitational force, or in order to balance the gravitational force with the restoring force of the torsion fiber. You can measure the strength of the torsion fiber. That's very easy to do. You just set the pendulum. You have it in a pendulum form, you oscillate it back and forth, and as the pendulum swings from side to side, that gives you the oscillation frequency tells you almost directly, it's like the square root of something like that, of the spring constant in the torsion fiber. So measuring the spring constant of the torsion fiber is pretty easy to do. You set it in oscillation, and it basically is one simple formula that gives you that result. And then when you want to then balance the gravitational force to the torsion fiber force, you already know what the torsion fiber force is, and so you can measure the deflection of the balance by moving these small masses, or in this case, moving the large masses relative to the small masses that are suspended by the torsion pendulum. Okay, so the arm stopped rotating when it reached an angle where the twisting force of the wire balanced the combined gravitational force of the attraction between the large and small spheres. So this is a large sphere, this would be a small sphere right here. By measuring the angle of the rod and knowing the twisting force, the torque of the wire for a given angle, which is fairly easy to show, or fairly easy to do, Cavendish was able to determine the force between the pair of masses. Since the gravitational force of the Earth on the small ball could be measured directly by weighing it, the ratio of the two forces allowed the specific gravity, meaning the gravity compared to per kilogram, of the Earth to be calculated using Newton's law of gravitation. So that is using that equation where this one, like that. So getting out big G from that measurement. So the first time this was done, he found it to be 5 times 10 minus 3. So he calculated the density of the Earth. His interest was in calculating the density of the Earth, and then you know the size of the Earth so you can get the mass of the Earth. So he calculated the density of the Earth, found it to be this amount, and then that's pretty much what the Earth's density is. It's a measurement of about like a 1% measurement, which is pretty good for an apparatus like this. No one had ever measured the mass of the Earth before Cavendish. This was the first time it was done. Let's see. There's some really nice CGs. Okay, couldn't run this thing on a space station to weigh it since it's not sphered. So you can measure the mass of the Earth by putting something in orbit around the Earth as well, because you know the size of the Earth. You can measure the altitude of whatever it is that you put in, and then you measure the orbital period of the object orbiting around the Earth. The problem is that, well, this is a lot easier apparatus to build than building a rocket ship that can put something into space. Okay, so again, right here, Cavendish timed the natural oscillation period of the balance. There you go, and that has a mousetrap on it. As it rotated slowly clockwise and counterclockwise against the twisting wire, a period of 20 minutes. So I was on an experiment that was similar to this. It was looking at a different phenomenon, but it was it still used the same basic design of a torsion pendulum. And the oscillation period in that case was 15 minutes. So we had like a 1,000-second oscillation period. And so that goes to show like how slow this thing is going to be twisting from side to side. Once you measure it, then you know the torsion coefficient, which is the spring constant of the wire that you oscillate in. So his measurement of big G, 6.74 times 10 to the minus 11. The accepted value today is 6.67 times 10 to the minus 11, so he's basically right there, right in the ballpark. There is a measurement of big G over time, so let's see if we can find the measurement of big G over time, because the value has fluctuated and the quoted errors have also fluctuated. So measurements of G over time. Gravitational constant over time. This is what I was looking at, the gravitational constant, again from the source of all human knowledge on Wikipedia. Right here. So from 1910, so this is basically for the last century, you can see that the uncertainty has shrunk over time, which is what you would expect as you improve your experimental techniques. But you also see that, okay, so some of the measurements have gigantic uncertainties, at least relatively speaking, and some of them have tiny uncertainties that are completely inconsistent with each other, right? So you have a variety of measurements in here where this one, the quoted error bars are so small that it's completely inconsistent with this measurement right here to a large extent, which implies that there are systematic uncertainties, systematic errors in the design of these different experiments, because big G, as far as we can tell, big G does not change, and otherwise it wouldn't be a constant. So we're assuming it's a constant unless you can demonstrate otherwise. But there are always systematic effects. There are always issues that come into play when you're making, especially very sensitive measurements, where even small issues can mess up your measurement. For example, one of the issues that I know, I'm not sure if it was for one of these experiments directly, but it was from the same group of one of these experiments, is that the definition of the inch has changed. The definition of the inch is like some number of centimeters, and they purchased a particular type of screw, and the screw was designed to, like, once you build your pendulum, you need to know exactly where all the mass is in the pendulum. I can show you an example of, like, here is a more modern version of a torsion pendulum. Let's see. So this is from the University of Washington group. So that's where I went to school, for graduate school, and I collaborated with Riley Newman on a different experiment. And so if we take a look, it doesn't look like it shows it here. So let me go back to University of Washington. See an image of the big G measurement at the University of Washington. So this is an example of the kind of pendulum that you would build today. So it's a slightly more sophisticated than the one that we saw from the Cavendish experiment. So here's the Cavendish result or experiment here. This is the torsion pendulum there. In this case, the torsion pendulum is, you know, about the size of a can, like a soup can, and it has these precision machined spheres that are on it. It's set on an apparatus that balances out a whole bunch of systematic effects that could creep into the apparatus. You have to worry about, you know, is there going to be some chair that's out of place? And there are, in these kinds of designs, there are often little screws that you can use to tune, like to balance everything, so that any machining errors that creep in, you can remove them by adjusting certain screws that will redistribute the mass to remove the gravitational effects of the machining errors. So there's always going to be machining errors whenever you make something, and so you want to be able to identify the machining errors that are going to cause you problems, and then you want to incorporate in the design some way to mitigate those machining errors so that it even with high precision machining. So in this case, the machining tolerances tend to be, you know, a couple of mils, like a couple thousandths of an inch. But you can even take it down by another factor of 10 if you have some way of balancing it with some movable part of the apparatus. So they'll have these kinds of screws on there. Well, it turns out that the manufacturer of the screw used a different definition for an inch because it's a machine that they'd had in place for a long time, and it was off by like 1 part per thousand or something like that. And so as they knew what the thread count was, and so they knew how much they needed to twist the screws to balance it out the way that they wanted, and they couldn't, like, it didn't work properly. And it turns out that they discovered that the manufacturer had used an old definition of what the inch was rather than the new definition of what the inch was. And as a consequence, all of the calculations were thrown off by a small amount. But they were able to pick it up in this with this kind of apparatus. Not necessarily this one specifically, but it was the same group. They've done a number of experiments using these kinds of things. And so these are extremely sensitive pieces of equipment. You need to be able to trim away systematic effects. It's like, so some of the systematic effects, I was on a similar experiment that we had to worry about was really, did we put the chairs back in the right spot? Is there water flowing in, more water flowing in the river that's nearby? Is there animals walking around outside? Is there water is the ground saturated with water nearby, because that changes the mass? In this case, in the case of the experiment that I was working on, it was they were using a cliff face as the mass that was attracting the torsion pendulum. And so if there's water in the cliff face, like if there's water soaked into the ground, then that changes the amount of mass that you're attracted to. And so you had to account for, you could see the rainy season versus the dry season by the changing mass of this piece of rock or the mountainside that we were operating next to. So this is an example of a more modern experiment to measure big G. Some of these things, one of the experiments in particular was done fairly recently, where they had a fiber, everything was chosen. They actually had, they had machined everything with a specific multiple. So they had a constant that was factored into all of their calculations, and they didn't know what the constant was. It was written on a piece of paper, sealed in an envelope. And this was Riley Newman's group. So that's one of the authors. It's not this particular experiment, but it was another one that was done by Riley Newman from the University of California at Irvine. And they had sealed it in an envelope. And then the idea was that they would make the measurements. They decided beforehand exactly how they were going to analyze the data. And then when they were all finished, they would open up the envelope, read the number, plug it into the formula, and then get their final result. And it turns out that they found a slight temperature dependence to the spring constant of the torsion fiber. And so when they ran it at different times, they saw some variation in the spring constant, which messed up their measurements. And so they reported actually two numbers. One of them was the one that they decided originally that they were going to do, and a second one was if they included the systematic effect of the temperature dependence of the spring constant of the torsion fiber, then they got another value for big G. And so that was a fairly recent result. But it goes to show that when you're getting to really high precision measurements, I mean, this one here, 6.6726 plus or minus, and then that's a part, that's like 5 parts per 10,000, half a part per thousand. These are very sensitive instruments, such that with these kinds of torsion pendulums, you can measure, for example, the weight of 1/1,000,000th of a postage stamp on the end of a pin that's stuck off to the side. Like, you can measure these extremely small torques as a consequence of the apparatus. So that is the measurement of big G, and it has been improved over time, but the original design of the Cavendish experiment is still being improved upon, both by new machining techniques and by new mathematical calculations that can go into designing some of the parts of the apparatus. So if we look again at the Cavendish experiment over here and see, it's basically just these spheres. One of the issues that you run into, as I mentioned, is if you have something out of place, then it's going to change how these spheres interact with it. There's going to be forces that they're sensitive to that are hard to control. And so you can design pendulums, you can design torsion pendulums to eliminate some of those effects. Part of it is by adding certain symmetries to the torsion pendulum. So if I go back to this one, You can see that it has a variety of holes. You can see that it has multiple layers in it. You can stack these balls in certain positions so that it eliminates certain forces and allows other forces to persist. When I was on an experiment, it was designed to look at a different thing. We had inverse square law of gravity, Washington, here. So that was the design, this one on the left, that was the design of our torsion pendulum. It was specifically designed to mimic, to some extent, a hollow sphere and a solid sphere. That should, if gravity works the way that you expect it to do, the hollow sphere and the solid sphere should have exactly the same gravitational field. But in this case, it's hard to do like a hollow sphere and a solid sphere, and so this is what we were able to manufacture. But if there's some weirdness to gravity, if it behaves a little bit differently than expected, then these would no longer work the same. It would no longer have the same gravitational force on the two sides of the pendulum. So it looks like it should be suspended along the axis of symmetry, but in fact, it's suspended from the side. And so you have like this somewhat imbalanced, it certainly looks imbalanced, torsion pendulum that's in there. So a lot of this improvement has come because of the advent of new computers, because of the advent of better machining technologies, in order to make different types of apparatus. So that is basically how Big G was first measured. It was measured by Cavendish using this apparatus in the late 1700s, 1780, 1797, 1798 by Henry Cavendish. And it's from there, ever since then, it's basically been incremental improvements in determining Big G, and as a consequence, understanding both how the Earth works and also like what the mass of the Earth is and the density of the Earth, and also determining the strength of gravity. So there you go. That is the Cavendish experiment.